All right, Calc 3, welcome in. It's Thursday, October 14th, and we are at the end of week 9. Welcome in. We have just finished 13.3, talking a bit about partial derivatives, the idea of taking a derivative of a multivariable function with respect to a single variable, right? Either x or y or z if you have it. And that was the idea of that was the idea of finding the change in at least one direction, right? As we're finding out, it's kind of hard to say what is the rate of change of a multivariable function. And that's because we've noticed last time that it actually depends on which direction you're going on your three-dimensional surface, right? It's like if I stand here and I look this way, well, it's sloped downward. But if I turn around, it seems like it's sloped upward. And so there seems to be a different slope depending on the direction that I'm looking. And that did not happen in Calc 1, right? It was rise over run, and it didn't have a three-dimensional surface. We were able to just say the tangent line is going in this way, right? But in 3D, it seems like there's multiple answers for the rate of change. At least there's different directions. In this direction, it's this rate of change. In this direction, it's this rate of change, and so on. We're going to get into directional derivatives soon, but for now, we are going to talk a little bit about what partial derivatives can do for us as far as applications, just a quick little applications thing. And one of the ideas that we talk about is differentials. So 13.4, differentials. So I want to remind us of what differentials were in Calc 1, how we used them, and what they were useful for, and remind you of the definitions and all that good stuff, right? So in Calc 1, we call Calc 1, suppose I have a function, okay, like this, f of x, yeah? And suppose I don't know much about this function, except I do know at x what's going on, right? So suppose I do know this value. So I know x and I know f of x, okay? Now, let's increment x a little bit. In other words, I'm going to bump x by a little bit. We usually call that a delta x. So I'm going to change x by a little bit, right? So of course, changing the function, changing the x value, has of course produced a corresponding change in the y function. It was at this height, and now it's at this height, f at x plus delta x, right? So bumping this much has caused a corresponding little bump, in this case, of this height going from here to this height, there, yeah? Now, in most cases, because I have a function and I have a formula for that function, I can calculate f of x plus delta x, no problem, right? No difficulty at all. So, you know, if this was like the function x squared, and you said, okay, I obviously know when x is 1, I get 1 squared, right? And if I bump x by, you know, 0.02, well, now I could just plug in 1.02 and then square it and then get my function value. No big deal. No big deal, right? And I could actually calculate that, no problem, right? Well, that is actually a problem if you start talking about transcendental functions, right? Functions that don't really tell you how they calculate themselves. Even for an example, right? I mean, I know what the square root of 9 is. I mean, exactly, I know what the square root of 9 is. It's 3, yeah? But do you know what the square root of 9.023 is, right? A little change in the x value here has changed the y value by how much, right? Without a calculator, you know, I'm going to just be able to give you the answer a little bit more than 3. Differentials allows us a way to estimate what that little bit more is without having to actually know what the function value is. Right? So differentials are going to allow us to change a variable and note how that changes this and try to approximate that. Now, what do you mean by approximate? Why do I approximate? Can't I just type that in my calculator? Well, yes, of course. Somebody could calculate that and get a a decent answer, right? At least an answer accurate to 8, 9, 10 decimal points, which are good enough for most everything, right? But there are some things where you might start to get into some trouble, right? So for instance, even like this, we know that sine of pi over 2, we know that exactly, right? But you don't know what the, well, let's see, pi over 2 is. Let's see, pi over 2 is 1.57. So then if I added like this to it, and I asked you, what is the sine of 1.59079? Yeah? Well, I don't know. You know, I don't know what that is. I took pi over 2 and I bumped it by 0.02. And now I'm asking, what did that change for the y? What did it change for the function value? And you see, I might know this exactly, but this I don't know. And again, you might say, well, I just type in my calculator. How does the calculator know? Right? How does it know? Because sine is not one of those functions that tell you how to calculate itself, right? I mean, the only reason you know sine of pi over 2 is by a memorized fact and understanding maybe a unit circle in that way. That's the only reason you know that the sine of pi over 2 is 1, right? And you have no idea how to do sine of 1.59079, right? Like if I had to do that by hand. No clue, right? No clue. Now, I do have a guess. I could tell you what it's close to. But do you see that I'm going to have trouble even calculating what this is without a calculator that has those algorithms built in? So this allowed us to get the idea of differentials. So in this case where it's hard, this is difficult to calculate, right? Especially if I was had to doing it by hand, right? What I can do is utilize the tangent line and hope that the tangent line will give me something approximately equal to this function that's hard to calculate, right? So for instance, in my picture here, I know that this is the actual change in y, right? In fact, we will call that delta y. Delta y is the legit actual change in y, right? But now let's say that I go ahead and I draw a tangent line here at the point where I know stuff about my function. You see that? I know that my tangent line does this at this point of the function. So I do have to know the x value, I do have to know f of x, and I have to know the derivative of f. But if I know those things, I can plug that in and get a tangent line. Now here's the hope. Look what happens on the tangent line when I go over delta x. Do you see that height? That goes from here to here. See that? That's not the actual change, but we will define that to be the differential of y. This is what the tangent line thinks that the y value of the function should be when you bump it by delta x. Do you see that? So you have the actual function, and it says it's up here. Then you have the tangent line saying, well, I predict it should be about there. And do you see how those two are kind of close? Those two are kind of close in value. So we hope that dy is approximately equal to the actual change in y. And that's how we can build a differential. That's what we want the differential to do. We want it to be what the tangent line will predict as the y value and use that instead. Why is that easier? Well, every straight line is easy to calculate, right? Every straight line has the form of y equals mx plus b. So I know how to calculate any value on any straight line. You tell me the slope, you tell me the y-intercept, I'm good, right? And so that is no calculation problem whatsoever. And like I said, the hope is that this is close to what the actual function is. Now, if I really bump delta x a lot, that's going to end me way over here. And now this tangent line is way off, right? This is the actual change, right? But the tangent line says this is the predicted change. So you can see that in some cases, if delta x is really large, right, these start to differ by a lot, right? So this idea banks on It really counts on the fact that delta x is close, is small, right? This is the same effect as if you zoom in on a picture, like on GeoGebra or something, on a graph, and you have a tangent line and you have the function. When you zoom in, it'll be harder and harder to tell which one is the tangent line and which one is the function, because when I zoom way in, it looks like a straight line, right? And that's a property of functions also, is no matter how curvy that function is, if I zoom in enough, it looks kind of like a straight line. Yeah. Okay. So in Calc 1, we defined what it meant to be an increment. Those were the actual changes. So we could define delta x to be the increment of x. This is actual change in x. Okay. And I want you to think that you have control over this, right? X is the independent variable, so you get to control the independent variable. You say, okay, X was 2, and now it's 2.1. I bumped it a little bit, so the delta is 0.1, right? You get to have control over delta X in this scenario, right? Delta Y is known as the increment of Y, and this is the actual change in Y, right? This you don't have control over, right? Because that's subject to whatever the function you were given says, yeah? So you don't really have control over delta y, right? It's dependent on delta x, right? The actual change in x, yeah? Now, differential of x. Now, for ease of notation, there is no real concept of the differential of x in this sense. We can say that the differential of x is the actual change in x. There's no need to approximate the actual change with a differential because we know the actual change. Remember, we were in control of it. So this was known as the differential of x. And that's what we can say for any, differential of x. And this is what we would do with any independent variable. The differential of x is no different than the increment of x in this context. Yeah? But in Calc 1, you learned a formula for the differential of y. So the differential of y, this change, according to the tangent line, has a really easy formula, and it was defined to be the derivative of f at x times the differential of x. And so this, we hope, is close to delta y. That was a little bit of a recap of the Calc 1 version of differentials. What I'm going to do now is upgrade this to a multivariable case, multivariable situation, right? So now the case becomes the following. Suppose I have, get this going. Suppose I have a function here, right? And I don't really know its formula, let's say, right? But I do know that when x is 1 and y is 1, that the surface is square root of 2, okay? And this is the shape that I have right here, right? Now let's say that I bump this, right? So let's bump this to, I'm going to bump x. It's currently at 1. I want to bump it by 0.01. And then I'm going to bump y by 0.02 negative. So that's going to be 0.98 in its new location. And then find its new z value, right? So that's going to be, in this case, I do know the formula, so I'm going to cheat a little bit just for visualization here. Okay. So let's see if this actually is worth looking at here. Let me zoom in. And you see that I have bumped the 2, right? And of course, the height has changed. There is a different height here. And I might not be able to calculate that different height very easily, right? Maybe it's a formula that's hard to work with, or maybe something else is going on and I don't have that formula. But what I have now is I've bumped the x and the y, and that's of course changed the height of the point, right? What I'd like to do is try to approximate that height. try to approximate what that height is. And instead of using a tangent line, let's use a tangent plane. Oh, did I delete my plane? I didn't mean to delete it. Oh, hold on. Can I undo? I can. Good. Uh-oh, now it's broken. What happened? Oh, I have frozen GeoGebra. No. I've sort of frozen it. It still allows me to select things, but it's not changing the visual here. Cute. Nope, it's not going to let me do this. Oh, no. I blew it up, folks. I blew it up. Okay. Let's do plan B. Hold on. I'll go to the textbook. I think they have a picture for us. Yeah. This will sort of work, I guess. Okay, so take a look here. Oops. Move this over here. Okay. Now this looks a little complicated, but go with me on this, right? What we have is now this situation. Here is the point xy, right? Point xy, see this in the xy plane. And of course, at xy, there's a height to the function, right? And so there's the height, there's the z value, right? Now, bump x by a change. Bump y by a change. Notice that there's two independent variables now. So there's two independent bumps that can happen, right? I can do an x bump and a y bump. That puts me in a new location at x plus delta x, comma, y plus delta y. And of course, that puts me to a new location on the surface, if I was to plug that in, right? Now, this height right here is the actual change in z. This is the actual change, right? It went from this height down here, and it climbed up to this height. That's the actual change. So we would say that that is the increment of z, right? Now, instead of using the surface, which may be difficult to work with, try using the tangent plane at this point. So notice that this is now a tangent plane, much like our tangent line, yeah? And notice what happens here. If the tangent plane says that it's this tall when I plug in the x plus delta x, y plus delta y. And keep in mind that finding things on a tangent plane is actually pretty easy, just like finding points on the line. Finding points on a tangent plane are not hard either, because that's the linear thing in 3D. Yeah? So we will call this the differential of z. And notice that it's the change in the x direction time the direction plus the direction of the change in the y direction, like this. And so what we're going to have is two sources of change. But what we're going to get, and hopefully is the truth, is that the increment of z is close to the differential of z. Now, in this case, it's really like emphasized. In practice, it's not this far away, right? This is really zoomed in or zoomed out to show you that there's a huge difference. But remember, in practical cases, this difference is very, very small, right? Very, very small when you zoom in, right? So anyway, let's get to defining what I mean by the differential of z. I'm going to define it as the addition of these two pieces, right? And these two pieces come from the two bumps that I made. I made an x bump and a y bump. And so bringing that together is going to allow me to add in and figure out what this is. And the hope, like I said, is this, that the delta z, the actual change, is approximately the differential of z. We hope that those two things are close. Okay, so let's go ahead and get writing our definitions down for this. So, definition of total differential. Okay. All right, suppose we have a surface z equals f of xy, and we have some delta x and delta y are increments of x and y. Okay. Remember, x and y in this context now are both independent variables. And so they can have independent nudges, right, of delta x and delta y. Then the differential, otherwise known as the total differential. Sorry, not yet. Then the differential of x and y are dx equals the increment and dy equals the increment. Right? Because they're independent, we control that. We don't need to approximate it. Let's just set the differentials equal to that change. Here we go. Remember, z is what we don't have control over because that's a dependent variable. So now I can say, and the total differential of z is dz equals the partial of z with respect to x times differential of x plus the partial of z with respect to y times the differential of y. Said another way, it's fx dx plus fy dy. See now, in Calc 1, right, we only had one independent variable. And notice how that reduces to a Calc 1 situation if we got rid of y. That the function, the dependent function, is equal to the slope in that direction times the change in x. But now that I have two sources, two independent variables, it's going to be whatever the change is in the x direction added to whatever direction change in the y direction. Yeah? And so that's going to be the total differential in that change of height. And so we get this formula. The differential of z is now two form. It has two terms, I mean. Yeah? Okay. And we can extend this for further and further and further. If I have a function, let's say if I have a function w equals f of x, y, z, and u, let's say, then I can define the differential of w to be the partial with respect to x, dx, plus the partial with respect to y, dy, plus the partial of z, with respect to z, dz, plus the partial with respect to u, du. See that? So the differential would expand like that if I had four independent variables. Right? So that would be the pattern of the differential. Okay, for now, let's go ahead and just practice calculating our total differentials. Right? So example, we have z equals 2x sine of y minus 3x squared y squared. Okay. All right. So in order to calculate dz, I better get the partial with respect to x and the partial with respect to y. Right? So let's go over here and do that. I can say fx is going to be the derivative of this with respect to x. That's going to be 2 sine y minus 6xy squared. Okay. And the partial with respect to y is going to be 2x cosine of y minus 6x squared y. Okay. So I'm now ready to assemble my total differential. It's going to be the fx part, 2 sine y minus 6xy squared dx plus the fy part, 2x cosine y minus 6x squared y dy. Okay? That's how we calculate total differential, right there. Okay. One more quick example. What if w equals x squared plus y squared plus z squared? We can calculate the total differential of w by taking the partial with respect to x. Now this one's easy enough. I'm just going to do in one shot here. Partial with respect to x is 2x dx. Partial with respect to y is 2y times dy. Partial with respect to z is 2z dz. And so there's the total differential of that function. Okay? Excellent, excellent, excellent. Then the book goes through a little bit of, you know how I keep saying that in practice we hope that, you know, the differential of z is approximately equal to the actual change of z. Now, the book gives a little bit of an argument as to why that is a reasonable thing to expect. Yeah. So let's take a look at this real quick, right? So, what this is saying is these are conditions that are sufficient to get differentiability. So one of the ways that you can get differentiability, right, it says if f is a function of x and y, where the partials are continuous, then f is differentiable on R. That means if f is differentiable on R, that means its differential is going to be close to the actual change in z. Here's how they figure this, right? They say this approximation right here is illustrated here, and dz equals, you know, partial z with x, delta x, plus the partial z with respect to y, delta y, right? And I'm not seeing this. Yeah, this is what I'm looking for. So notice that this delta z here equaling fx delta x plus fy delta y plus this little leftover bit, epsilon 1 delta x plus epsilon 2 delta y. If these little errors go away as this gets closer and closer to the point that you want, then do you notice that these go away and it converts itself into the total differential, right? That's what we actually define to mean differentiability, is if that happens, right? Now that's not guaranteed to always happen, right? Because you might get real close to the point, right? Shrink the change of x, shrink the change of y to 0 and 0, right? And you might end up getting that this does not go away, right? Right? That this just doesn't work this way, right? But in a differentiable function, it does. And so these will wipe out and leaving you with the exact differential there, right? I'm not going to spend too much time on that. But the idea is this, is if the function is differentiable, right, it means that these differentials are close to the actual change of the variable around the neighborhood that you're at, okay? That it does go as close as you like, as long as you get as close that you can to the point, okay? This means that we can use these differentials for approximation purposes in a nice, reasonable way. So for instance, one of the things we can do is approximate function values, right? Like I was saying earlier. So let's go ahead and look at an example where I use a differential to approximate values of functions. So example here, I'm going to use the differential, okay? Differentials dz to approximate z equals the square root of 4 minus x squared minus y squared from the point 1, 1 to the point 1.01 comma 0.97. Okay. So pretend for now that I don't want to grab the calculator to do just the square root business here, right? That I want to just sort of do mental math if I can do it. Okay. That doesn't mean I'm not going to use a calculator to help me even with basic arithmetic, but assume that I'm very shaky with finding square root values. I do know nice ones, right? I do know nice ones, and I do know, that I can just keep it as exact. All right. So here's what I want to do. I want to approximate what is f at 1.01 comma 0.97. Okay. I want to know what that value is, approximately anyway. So here's how I can set this up. Go to the nearest point where that is nice. And so notice that that's 1, 1, right? So let's say that x is 1 and y is 1. And let's think of the delta of x to be 0.01. Do you see that? That makes this 1.01. That would be x equaling 1 with a change of x being 0.01, getting me to the new location. Okay. Then y starts at 1, and then delta y looks like it's going to be a negative 0.03. And you would agree maybe that this is now describing 0.97, starting at y, and then applying a change in y of this much. Okay. Now, here's how I can do this. The change in z is going to be approximately equal to the differential of z. The actual change that I want to know, because I know x changed and I know y changed, so I know that z changed, and I want to approximate that. How do I approximate that? Using the differential. The differential of z in this case is going to be the partial with respect to x times dx plus the partial with respect to y dy. So let me calculate those things. I'm going to look at this and take the derivative with respect to x. This is stuff to the half power, isn't it? So a half is going to come out. Let me do this over here. A half is going to come out 4 minus x squared minus y squared. Drop the power by 1, so power is negative 1/2. Times the derivative of the inside, which is negative 2x with respect to x. The 2 will cancel with a half. This square root goes downstairs, and I have negative x in the numerator. So I have negative x divided by the square root 4 minus x squared minus y squared. That's fx times dx. Okay. Plus, take the partial with respect to y. It's going to be the similar derivative, right? This part's the same, but now I'm multiplying by the derivative of the inside with respect to y. So now it'll be negative y, 2y, negative 2y. The 2's will cancel again, but leave me a negative y instead. So I get this. And I know this looks complicated and all, but remember that x and y are nice numbers, are really nice numbers, right? So what I get here is going to be the following. This is just going to be negative 1 divided by 4 minus 1 minus 1, which is square root of 2, times dx, and then minus or plus minus 1 divided by square root of 2 dy. Okay? Right? Now, even back in the day, if I didn't have a calculator, they did know the square root of 2, even without a calculator, right? And so what I can do is just plug in the dx and the dy. The dx is going to be 0.01. And the dy is negative 0.03. Okay? Now that theoretically could be done by hand because the square root of 2 is 1.41-ish, right? And so technically speaking, that could totally be done by hand, right? It's not the nicest calculation to do by hand, but it can. It's not like I'm asking you for the sine of 1.62543, right? This is at least something I can do by hand. but I'm not. I'm going to cheat and use the calculator to do this. Negative 0.01 divided by square root of 2. And then minus 1 over square root of 2 times negative 0.03. So yeah, so I get a result of 0.014142 and so on. Okay, so let's recap what I just did. All right. If you bump x by this much, and if you bump y by that much, I'm approximating the actual change in z to be this much. Okay? So getting back to f at 1.01 comma 0.97, what would that value be? Well, f at 1.01 comma 0.97 is going to equal f at 1,1 plus the change in z, which I'm approximating with the differential of z. In other words, this is what it was, and this is the approximate change in that height. So I'm going to take what it was and add in the change to get the new height. Yeah. Well, f at 1,1 is square root of 2 plus 0.014142. So my new function value is approximately equal to this. Again, square root of 2 is something everyone knew back in the day, and they wouldn't think anything of it, of adding this as decimals. So I get an approximate function value of 1.4283 and so on. So this is what I think is going to happen when I plug in 1.01 and 0.97 into the function directly. I'm going to do that now. I'm going to find what that actually is thanks to my calculator that doesn't mind finding square roots of weird numbers, right? And so that way I can compare, right? Now remember, in the real world, I might not be able to do this, right? This is a nice textbook thing where I can approximate a thing and then actually go and calculate the thing exactly and compare how my approximation was, right? That sometimes can't happen in real life, right? Sometimes I'm not able to do that. This is going to be what? This is the square root of 4 minus 1.01 squared minus 0.97 squared. So I'm going to do that in my calculator to compare. 4 minus 1.01 squared minus 0.97 squared. And I end up with a result on the calculator of 1.42793. So not bad, right? Not bad for something that I could have done by hand, right? Whereas this was involving decimals, squaring them out, and then subtracting, and then doing the square root of that weird number. This at least had the possibility of being done by hand. And so what I can do now is that this is the approximate, and I did pretty well. It's 1.42, and it starts to differ in the third decimal place. Here I had 8, here there's 7. Okay? So decently close, probably for, a variety of work. Maybe don't do medical stuff with this where it needs fine precision. But hey, this seems like a decent approximation overall, yeah? All right, any questions from the live group here from what I'm doing? We're doing okay. Let me know if you have questions, or let me know if you don't have questions. Let me know. Okay, nope. All right. No questions. Good. Okay. Now, a nice application of this also is predicting something called propagated error. Okay, propagated error. This is error that sort of builds on itself. Oh, A, propagated error. This is, you know, have you ever done a math problem, right? And you made a small mistake early on, right? So there's a little bit of error. It was off by, you know, just a little bit. But then you kept using that number, right? And calculating with it, and then did another calculation with that, and then did another calculation with that, and then did another calculation with that. And at the end, you're way off, right? That small little nudge, if you will, a small delta x, if you will, a small error has caused a great expansion of error as it goes through the calculations. And at the end, you're like, wow, I'm way off, right? That's the idea of propagated error, right? So the question is, if I make small errors in something I'm measuring, right, which is a big deal if I'm actually creating something, right? It's like, if I'm actually creating something, I have to really worry about, you know, manufacturing error, right? Like, you know, it says I need this to be 50 centimeters, but you know it's not going to be exactly 50 centimeters, right? There's error, right? Even in my measuring, there's error, right? Let alone the construction and whatnot, right? So the point is, can I sort of estimate like a worst case scenario, right? So suppose I'm trying to create like this rectangular box, right? And so I have this rectangular box like this, right? And let's see. They tell us in this problem here that the possible error in measuring each dimension, each dimension is plus or minus 0.1 millimeter. Okay. All right, so whatever tool I'm using to measure this or to create this, however it goes, yeah, plus or minus 0.1 millimeters. Okay. Now, the dimensions of the box, let's go ahead and let's see. Oh, I want to match my letters here to match the box than the way I've drawn it. Oop, this is not to scale, folks. Just a warning, not to scale. They call Z the height, they call Y the width, and they call X the length, I guess. Would that be called that? Right? Okay. And we're told, or I measured, X is 50 centimeters, Y is 20 centimeters, and Z is 15 centimeters. That's what I measured anyway. But remember, my measurement can have error. Right? So the question is, if I use these measurements to calculate something, I'm going to propagate error into that new calculation. And I wonder how bad the worst case scenario would be. Right? We can use differentials to help us with this. This isn't the only way, but this is one use for differentials, right? So for instance, what if I wanted to calculate the volume of the box? Right? We know that the volume of the box would be X times Y times Z. That's a function of three variables, three independent variables, right? Length, width, height. What I can do is think of this error as possible delta X, delta Y, delta Z, yeah? And if I have all of those little nudges, what is the worst that the volume will do? Yeah? In other words, let's calculate the differential of volume to predict what the change in volume would be if I have these measures and these changes that happen. Okay? So differential of volume, so dV. Well, that's going to be the partial of this with respect to x, that's y times z, times dx, plus the partial of this with respect to y, which is xz dy, plus the partial with respect to z is xy times dz. Okay? And this sort of does the heavy lifting for me, right? It sort of puts in the error for me, I see how the error plays a role in this, and then I see that it has to multiply by the area of one of the faces. Now that is a deep connection that I might not have known from just looking at this problem, right? But the math is telling me that this change in volume is going to be the same as the bump in x times the area of this front face, right? Y times z, plus the change in y times the area of x times z, plus x y dz. So the change in z times the volume of the floor, the area of the floor, right? Face. So in essence, this becomes a plug-in problem. Do be careful with units. They're being sneaky here. Notice that the measurements are in centimeters and the error is measured in millimeters, right? And so 0.1 millimeter is plus or minus 0.01 centimeters, yeah? Okay. So here we go. We just plug in. Here's 20 times 15 times plus or minus 0.01 plus x is 50, z is 15 times plus or minus 0.01 plus x is 50, y is 20, and dz is plus or minus 0.01. Right? And you can kind of see that the plus or minus 0.01 is like a like term. So I'm just going to count how many I have here, how many I have here, how many I have there, and then combine it into a total number of plus or minus 0.01s, right? So that's going to end up being 20 times 15 plus 50 times 15. Another way to think about it is factoring out the plus or minus 0.01 plus 50 times 20. So I get 2050 times plus or minus 0.01. Okay? Doing that calculation gets me a plus or minus 20.5 cubic centimeters. All right? So a tenth of a millimeter error, or a 1/100th centimeter error in each of the dimensions, could provide up to 20.5 cubic centimeters of error in the volume, right? Now that is kind of nice to know, sort of, it's almost like a worst case scenario, like I said. That's if each one of these tolerances have been met, right? Have been surpassed even, if you will, right? And so that is my predicted change in volume, right? So there we go. So that was one of the questions. This is how much the propagated error would be, right? 20.5. Now the question becomes, is that a lot? Is that not so bad, right? Saying something is 20.5 in isolation, well, that doesn't help, right? I mean, 20.5 could be a lot of something, right? And it could be not a lot of other things, right? And so it's relative speaking, right? So I always use this example, right? Suppose I'm in NASA and I design this project and I shoot a rocket that's going to land on the moon, and my target is, I don't know, 10 square meters or 10 square miles, right? Or something like that. And I hit it like 4 feet from center, right? 4 feet from center. And you're like, man, you were right on, right? That was like ridiculously accurate, right? Shooting a rocket from Earth to get to the moon, to then land on the moon and only miss your target by 4 feet. That is #nailed it. Yeah, right? Now, on the other hand, if I'm your doctor, your surgeon, do you see where I'm going with this? And you had to have some shoulder surgery. Okay. And I said, after you recovered and came to, I said, good news. Good news. I was only off by 4 feet. all of a sudden you really care about that 4 feet of error, right? That's a little off from the shoulder, right? 4 feet away, yeah? But 4 feet on a target of the moon, really close. In other words, relative error matters, yeah? So don't get into the trap of saying, wow, that sounds like a lot of error. Well, is it a lot of error? It might not be relative to what you're measuring against, yeah? So that brings us to a quick little concept called relative error. In other words, is this a lot of error, relatively speaking? What's the percentage error sometimes people will talk about? And so it's going to be very good to talk a bit about the differential of V divided by the volume. In other words, is this a lot of error out of the total volume? We call this relative error. Okay. And allows me to see sort of relatively how it's going, right? Right. So my relative error in the shoulder example is ridiculously large, right? Because my surface area is small compared to the surface area of the moon, right? And so 4 divided by surface area of the moon is a much, much, much smaller number than 4 divided by my surface area, right? So, yeah. So here we go. Plus or minus 20.5 divided by the volume at that location. Now that's going to be x times y times z. So that's going to be 50 times 20 times 15. And going ahead and doing that gets me 0.00136, etc. Right? Now, percentage error would be just this number in a percentage. So we're talking about a percentage error of 0.1%. Right? And now you can make much more informed decisions on that. You can say, oh, I'm off by just 0.1%. I'm probably okay with that in a manufacturing situation. Yeah, that's probably okay. Now that doesn't mean it could happen that all of a sudden I get 20 more cubic centimeters, so 20 little cubes, right? And that actually does add to my volume, right? So I might have to make sure that my packaging, whatever I'm packaging this thing, can withstand this sort of error in the process, right? But for comparison's sake, I have a percentage error of 0.1%. Okay, so some places might be like, well, we need a tolerance less than 5%, we need error less than 5%, we need less than 1%, need it less than 0.1%, whatever, right? So anyway, now you can make a more informed decision relative to the situation at hand instead of just saying, oh wow, that looks like a big number. Awesome. Okay, that finishes differentials. So a couple of tasks that I want you to be able to do in the differential section is to approximate function values using a differential, right? And then doing propagated error, much like the problem that I just did. Those are the two sorts of applications that you can expect from the differential section, okay? Now, I'm going to move on to 13.5 here. 13.5 I'm not covering very deeply, right? But it is called the chain rule for functions of several variables. So we are going to get a little bit of a taste of what it means to talk about the chain rule in higher order derivatives and our higher order functions and things like that, right? So 13.5, talking about the chain rule for functions of several variables. Okay. Now, one thing about the chain rule, right, that you need to remember from Calc 1. We are definitely in the part of Calc 3 where everything's like, remember in Calc 1 what you did? And people are like, no. Okay, but we're going to act like you do, and I'm going to remind you anyway. Right, but anyway, from Calc 1, we had a function, right? And I wanted to take its derivative, but that function itself, sorry, let me collect my thoughts on this. Hold on one sec. What am I trying to say? Let's see, I had f of g of x, right? And I wanted to calculate the derivative of a composite function, right? And a function plugged into another function, right? So what I might do here is say, well, okay, let's call u g of x, right? So in one perspective, f is a function of u. Right? I could just now say this is f of u. And yeah, it says fu. Anyway, f of u, and then u itself is a function of x. So if I was to like make a picture of that, right? If I was just to make a picture of that chain, it's like f, okay, is a function of u, and u is a function of x, right? And we learned how to take the derivative along the way, right? So now I can actually talk about what is the derivative of f with respect to x, right? That's what we were interested in Calc 1. We're saying, hey, what's the derivative of this function in terms of x? Not this intermediate, right? And so we were interested in saying, okay, dy dx, if we call, f equaling y, like that, what is that derivative equal to? Well, it's equal to the derivative of y with respect to u. And then we learned it was multiplication times the derivative of u with respect to x. And that was the chain rule for a single variable function. It says I could take the derivative of this function with respect to the ultimate variable at the end of the path. I could go through this chain instead. I could say, oh, the derivative of this whole thing, f with respect to its ultimate variable, is the derivative of f with respect to the intermediate variable times the derivative of the intermediate variable with respect to x. Right? And we sort of said this in different ways in chain. We might not have said it this way, but we sort of hid the u and always called it like the inside function. I use the word stuff a lot when I say this, right? And so, but the idea here was like if I wanted to take the derivative of 3x squared plus 5 raised to the 75th power, right? I'm thinking of this as f of u, which equals u to the 75, and u equals 3x squared plus 5, right? And what this says is I take the derivative of this function with respect to u and then multiply by the derivative of the inside function. And so if I say the chain rule is dy dx equals the derivative of this with respect to u is 75 u to the 74 times the derivative of this with respect to x, that's going to be 6x. And then we know what u is equal to. U is just this stuff. So 75, 3x squared plus 5 to the 74 times 6x. And that's how we utilize the chain rule in Calc 1, right? But we never really drew this picture. We didn't really have to, right? Now, I want to introduce you to this multivariable situation and how we handle chain rules when there's multiple paths that one can go down, right? In the Calc 1 case, there was only one path, right? One path through one intermediate variable. Yeah? All right, so let's go ahead and do a scenario. Now, suppose I have a function w, and it's a function of two variables, x and y. Okay? But let's say that we further know that x is really a function of t, maybe time, right? And y is a function of time, probably different than x's function, right? Right? So in other words, w can be thought of as a function of two variables, x and y, right? But in another viewpoint, do you see that w could be thought of as ultimately as a function of t? I could think of this as f of x of t, comma y of t. And then that means that this is just a bunch of stuff with t. So I could have a variable, a two variable look at this, or a one variable, single variable. It's just a matter of your perspective, isn't it? All right, so in one perspective, two variables, x and y. In another equivalent way of looking at it, I can think of it as a single variable. But wait a minute, if I can think of w as a single variable function, couldn't I then demand what is the derivative of w with respect to that single variable? In other words, can I follow the chain through x and y down to t? So let me show you this picture now, right? W stands at the top, and w is a function of x and y, and x is a function of t, and y is a function of t. And you see, it makes sense to ask what's the derivative of w with respect to x and y, that's for sure. But it also makes sense to ask what's the derivative of w with respect to t. So how does the chain rule compensate in this case, right? So here's how this works. When you go down the path, you multiply the derivatives as you go. So do you see this is like the partial of w with respect to x. This is dx dt. Right? So think of these lines as doing the derivative, right? So w, the derivative of w with respect to x, that has to be a partial because w has two variables. But then x is a single variable, so this is just dx dt. This will be partial of w with respect to y, and then this is dy dt, like that. Now, once you have your paths, you add the contributions from each path that ends in the letter you want. So we want both of these paths because these both end in the variable t. So my chain rule for this case is two pieces. It's going to be partial w with respect to x times dx dt plus the partial of w with respect to y times dy dt. That would be the chain rule in this scenario. See that? And so the chain rule changes depending on, the scenario, how many variables a function has, and how many variables those functions are functions of, right? Let me do another example here. What if I had a function like this? What if I had w equals f of x, y, and z, and then x is a function of time, y is a function of time, and z is a function of time. Okay? So in this case, my graph, my tree diagram, would look like this. Here's w. I make three branches for the x, the y, and the z. And the x, the y, and the z all end in t. See that? So do you see how I'm going to have three terms? Because there's three paths that end in t. So if I want to say, okay, good, I want to find the derivative of w with respect to the ultimate single variable t, I have a formula for that now. The chain rule would say that it's partial w with respect to x times dx dt plus partial w with respect to y dy dt plus partial of w with respect to z dz dt. So yeah, the chain rule gets a little bit more complicated in higher dimensions, doesn't it? Most definitely. But it's really kind of easy to actually put it down the pattern, right? Because it's a tree diagram and you just sort of do that same pattern, right? I'll end the video with another scenario. Let's say that w is a function of two variables, x and y. But now x is also a function of two variables. Let me get suggestion for letter here in your book. Yeah. So suppose x is a function of s and t, and y is a function of s and t. Okay? So according to my tree diagram that I'm going to write, I would have something that looks like this. W at the top branches off to X and Y. But X and Y branch off to two things, S and T, S and T. Right? So do you see that W has two viewpoints? I could view W as a function of two variables where those variables are X and Y. That's one way to look at W. I also have another look for W. W is really a function of two variables that are named S and T. So W really has two ways to look at it, right? And the chain rule is all about asking how does the rate of change of this with respect to the ultimate variables that they are. So in other words, I could ask now, what is the partial of W with respect to S? Do you see that? And notice it's a partial derivative because now even W is still in both viewpoints, it's a function of two variables. Right? So the chain rule is done in the same exact way. We're going to multiply as we go down, but notice that in this case, we only have two branches that end in S. So my chain rule is going to be the following. Partial of W with respect to X times partial of X with respect to S. That's going down that branch. Plus partial W with respect to Y times partial Y with respect to S. And so that's the partial of W with respect to S. And I can find another partial, right? I could ask what's the partial of W with respect to T? That's the other variable. And so I can follow the same pattern there. Just follow these two branches. So I'm going to get partial W with respect to X, partial X with respect to T, plus partial W with respect to Y, times partial Y with respect to T. And so that is how the chain rule would work in that case. All right? I think that's a good place to end. I'm going to do an example of chain rule, not too much, but it does tie in with implicit differentiation from Calc 1, so I want to bring that up next time. But that does sort of finish the concept of the chain rule, what I want to do with it. Not very much, just that you know how to create them, and the chain rule changes a look when it's in higher dimensions, yeah, more with multivariables. Okay, that means we will be covering 13.6 next time, which gets into one of the most important tools in multivariable calculus, and that's directional derivatives and, more importantly, gradients. Gradients are going to be the closest we ever get to answering the question, what is the derivative of a multivariable function? And we're going to find out that the answer is not too simple, but the answer is not too difficult either, but it ends up being a vector. Interesting. I guess we'll have to talk about that next week, all right? So until then, hope you're doing well, staying healthy and happy. Looking forward to checking in with you on Tuesday. Be well. See you next time.